Okay, welcome everyone to my continuation of what is algebraic graph theory. Today we continue with polynomials because everyone likes polynomials. If you don't like polynomials, I feel very sad. I certainly like polynomials a lot. And this one is actually quite unique, so it's quite universal in a certain sense. And this one is the Tutte polynomial, which we have seen last time, and I'm going to recall anyway. So kind of everyone discovers the same polynomial, which is the slogan of this talk here, of this video. So let's have a look. First, let's recall what it is, and let's me admit a little bit of a failure. So last time I denoted the Tutte polynomial by p, and of course notation doesn't really matter, but I would rather like to denote it by t. So p is the chromatic polynomial with one variable, and t is the Tutte polynomial. So yeah, sorry, I should at least be consistent with my own notation. But anyway, t will be the Tutte polynomial. And remember that recall that it has two variables. And the definition here of the Tutte polynomial involves always this type of deletion and contraction, where you give a certain polynomial to each tree, and whenever you see a loop, you put in the same the other scale as the next variable y. So here's another loop. And this gives you the deletion contraction definition of the Tutte polynomial, which is written down here again. Okay, that's what we have seen last time. A Tutte polynomial, very, very great polynomial. And it satisfies two properties. I won't go too much into details into this one here. We need it later, but kind of ignore it. But the kind of more straightforward property of the Tutte polynomial is if you have well, maybe I draw a nicer picture. If you have a graph G here and another graph H, whatever, something like this, and you take the disjoint union of them and you compute the Tutte polynomial of those, then the disjoint union will be turned into multiplication of Tutte polynomials. So essentially what this is saying is it's enough to know the Tutte polynomial on connected components. Okay, and the question I would like to address is how unique is a Tutte polynomial with those properties. As I said, I will need this one as well, so you need it to get the statement correct, but ignore it. The point is here, I say that it is defined on connected components, and then if you have a non-connected graph, you just multiply, and otherwise you have this deletion and contraction property. And we want to investigate how unique this polynomial actually is. So in some sense, was it a coincidence that it was discovered, or could we have discovered it instead of Tutte? Yeah, we'll see. Okay, so and before I can make a formal statement, I would need I need certain notion from graph theory, which is a minor, which turns up very, very often. So a minor is a certain construction from a given starting graph G, and H here is my minor. And it's just saying that I can, starting from G, I can delete edges. So those dashed ones here are deletion of edges, and also vertices, right? So I can delete edges and vertices. So vertices is missing here, edges and vertices. And I can also contract edges. So I can contract here along this edge, and I get this graph H. Here's another one. I can remove this edge here, and then I can contract along this edge, and this edge here will become this edge here because I'm identifying those two vertices. And let's call them minor. It looks like a very strange construction, but a lot of properties in graph theory are actually minor closed. So what we really want to look at are classes of graphs which are minor closed, meaning if, well, my class is something like this curly C, so if my graph is in curly C, then all of my minors should be in curly C as well, right? It's minor closed, a minor closed family of graphs, so minor closed classes. And there are quite a few minor closed classes. There are a lot of minor closed classes. The most prominent one is probably that all graphs, or for this video, all finite graphs, are minor closed. That's kind of not a very exciting example, but just to make sure here. So all graph is a minor closed property because the minor of a graph is a graph. That's all I'm saying. A little less obvious, but also if you just look at the definition, it's also not so terribly difficult. If you can embed your graph in the plane, so you have a planar graph, then the same property holds for all minors. And that's where originally the notion of a minor came from. It's related to detecting planarity. In a very similar way, so all graphs that you can embed on a fixed surface, here like my torus, they are also form a minor closed family. Because look at the embedding of my graph here. As soon as I delete an edge or contract an edge, whatever graph comes out will be still embeddable on my little torus. So minor closed families, there are quite a few minor closed families. That's all I want to say. And kind of what I would like to study now is how unique are those properties for minor closed families. And why do we want minor closed? Well, look somehow at this picture. What we really do is we delete edges and contract edges, which is, let me go one step further, somehow the definition of a minor anyway. So kind of to stay in the correct clause, we want this property of being minor closed. And then this statement is quite beautiful, actually. So the Tutte polynomial is universal. Or formally speaking, that's all you need to remember, essentially. Or formally speaking, whenever you have a graph invariant, which satisfies deletion contraction, the product property, and some normalization nonsense, you can ignore the normalization nonsense, then it's actually a specialization of the Tutte polynomial up to some overall scaling. And the overall scaling is what we have seen, for example, for the chromatic polynomial as well. Chromatic polynomial is a specialization of the Tutte polynomial, and it satisfies those properties. And here you're really free to choose your scalars A and B, some scalars, and you can make that even more general. You don't need to work with polynomials. You can do that for some ring or something. So it's quite a strong property of being unique, universal in that sense. So whenever you have deletion and contraction, whenever you have the product, so you know it on each piece by the deletion and contraction, and you know it on the different connected components by the product formula, then it is a Tutte polynomial up to specializations. So for minor closed, we can, for example, just take all finite graphs, and it says that whatever kind of polynomial you will come up with satisfying those properties, like the chromatic polynomial, it will be a specialization of the Tutte polynomial, which explains somehow why I would like to stress the Tutte polynomial so much, because it's kind of the unique graph invariant in some sense. Okay, let me talk about this uniqueness a little bit more in a more vague sense. So essentially what this means is that all graph polynomials are specializations of Tutte. All, of course, in quotation marks, because all essentially means you satisfy those properties. And clearly not all graph polynomials will satisfy those properties, but quite a few will. And kind of what I would like to say here, it's kind of a universal graph invariant. It's a universal graph polynomial, which makes it interesting kind of by definition. So if you have seen universal properties and categories, if not, ignore it. It doesn't really play a role. But if you have seen them, then universal defined something defined by universal properties are always kind of very important. And in particular, the universal property in words is somehow saying that you or we or everyone could have discovered this polynomial or this whatever kind of object because it's universal. So eventually you will write it down, right? So if you're studying this problem, eventually you will write it down. Which is not saying the idea of Tutte wasn't good. It's actually a pretty brilliant idea, but it's kind of different in the following sense. Let me try to be a little bit hand wavy here. Not that I'm never hand wavy, I'm always hand wavy, but anyway. So if you think about something like the proof of Fermat's last theorem, then it's pretty clear what you want to prove. Fermat's last theorem, which is kind of very old, whatever, 300 years old, goes back to Fermat, but it's really not clear how to do that, right? So that's the whole point of Weyl's proof, right? It's really brilliant. The proof itself is a point, but coming up with a statement is really not all that difficult. And universal properties are kind of exactly the opposite. So universal properties is essentially as soon as you know what to do, everyone will come to the same conclusion. So the whole point about why Tutte was so brilliant is to just have the idea to do it. As soon as someone tells you do it, everyone will come up with the same conclusion. Anyway, so that's kind of what the universal property is. So you, we all, everyone could have discovered the Tutte polynomial, which also explains why it is so important and appears everywhere, right? So Tutte, a universal graph invariant, and it's clearly important to kind of study it because it kind of turns up just as a universal object. So if you like category theory, as I said, it's like a universal object in category theory. If you don't know category theory, doesn't matter. Think of it as being something like, as soon as someone tells you to study X, you will discover it, because that's what the kind of the universal property is saying. Anyway, I hope you enjoyed this video, and I also hope to see you next time.